Okay, now, again, we have incline at angle alpha, mass M1 here, mass M2 here. We're going to assume that the system is stationary due to friction. So the question is, what's the minimum value of the coefficient of static friction? Static friction because the thing is stationary. If we do a free body diagram for mass M1, what do we have? We have M1G, we have tension in the string, the normal force, and frictional force. And these forces have to be in balance so that the frictional force is going to have to be equal and opposite to the tension force. Now, intuitively, you know, well, it's not equal and opposite to the tension force because you've got a component of gravity in this direction. And, of course, you have free body diagram for the mass M2. And the tension in the string acts in the opposite direction. In other words, tension in the string at this end tends to pull the string shorter, which means it's going to act in the vertical direction on this mass. Frictionless, light frictionless pulling, so no friction there. And thus, the tension in this end has to be equal to the tension in this end. This implies that the tension is M2G. So from this free body diagram, so now we can take this diagram here, I'm going to write my frictional force a little bigger than my M2G. Not enough bigger. We have the normal force. If we put our x-axis in this direction, then we can project our gravitational force onto the two axes. And let's get colorful with that. Let's go ahead and say, okay, this force is here. Now this force has a component in this direction. And And that's gonna turn out to be M1G sine theta. You wanna make sure you understand why that is. Actually, yeah, that's right. I had to stop for a second to make sure I'd done that right. Okay. Now M1G cosine theta here. And now we can cross this out. And now the normal force and this force are the only forces in the y direction. So this leads us to the picture magnitude of this force is M1G cosine theta. Magnitude of your normal force also has to be, I'm skipping some steps there because we don't have time to do everything in detail. If you want to write these forces as vectors, then this would be negative M1G cosine theta times J vector, and positive M1G cosine theta times a J vector, because these two are the only vertical forces and we're in equilibrium on the incline. And we're y direction equilibrium. The motion along the incline has to be in the x direction, the way we tilted the axis. That's why we tilt the axis. And I assume you already know that because you've done a number of problems of this nature. Okay, so now we have just M2G here. And the force of friction here. What do we know now? We know I had my M2G here, and I did not include my horizontal component here. So, horizontal component of the gravitational force, which was M1G sine theta. So now we have the frictional force M2G M1G sine theta. And it's stationary, so it's in equilibrium. We know that the frictional force is in the negative x direction, and that these two forces are in the positive x direction. I'll factor the acceleration of gravity out. The other thing we know is that the force of friction is less than or equal to US times the normal force. And I said mu s and I wrote mu2. S's and 2's have similar squiggliness, but not really. And here I'm writing a 2 again, but I'll change that to s. Okay. Mu s times f norm. And so the force of friction has to be less than or equal to this, but of course this is normal force is just m1 sine theta times g. So if we put these two together, this expression is less than or equal to this expression. I said here, what's the minimum value of mu s? And I should have asked for the maximum. Wasn't thinking when I wrote down minimum. Actually, no, that's not right. I mean, if I solve this, okay. Look at things cross-eyed. We are trying to find the minimum. Okay, so we get this, and we then divide that out. And we get this. And this is going to be our minimum mu s. Because mu s has to be at least this big. Does this make sense? Well, one thing makes sense is the bigger M2 is, the more friction you're going to need to keep this thing from sliding, right? So bigger M2 will result in a bigger minimum. Okay? This isn't right though. Something's wrong here. Because if M2 is 0, then you get mu s greater or equal to 1. Doesn't depend on theta. So something is amiss in the analysis. Let's go back to where we get the M2G plus M1G. That's going to be M2G and M1G sine theta, which is just the component here. Frictional force is coefficient of friction times normal force. Normal force is this. Well, we're out of time. So something's amiss here because asymptotically, as M2 approaches 0, we know the required coefficient of friction does not approach 1. Okay, so we have somebody offering a suggestion here.